So we're going to talk about directed graphs. Okay, so a directed graph, or actually we'll generally use the term digraph, short for directed graph, digraph. So basically it's a graph where the edges have a direction. They go from U to V or from V to U, or actually both are allowed simultaneously. Let me give a formal definition, kind of like the definition for graphs that we had originally, but these are not that hard to deal with. So directed digraph D, usually use D instead of G for digraphs. Again, it's two sets, a vertex set and what will be an edge set, is a vertex set V. So it's a finite, again. So it's a finite set V. Let's actually write it this way. Let's not even name it yet. So it's a finite set V of vertices. That's the name of this set here. And a set E of, so in graphs, the edges were pairs of vertices, right? We just grab pairs of vertices with no order. Here we'll grab ordered pairs of vertices. That's the only difference here, okay? So it's a set of ordered pairs. Ordered pairs are ordered two element sets of V. And these are called arcs. Okay. Usually in digraphs, instead of using the term edges, we'll use arcs just to re-emphasize we're talking about digraphs as opposed to edges. Okay. But it's okay to call them edges as well. All right. And for a fixed D, as before, we use V of D and E of D for edges, vertices, and arcs of a digraph D. Okay, just to refer to those specifically. Okay, and so let me draw a couple examples here. This is very simple here, but there's one important point to emphasize. So here's a couple examples. There's a few in the notes as well. So let's say we have these four edges or arcs, and they're oriented as well, like in this nice circular fashion here, right? So I draw the arrow on the arc there just to emphasize, because right, it's an ordered pair of vertices. So it, like before, these arcs include two vertices. They have two endpoints, but they have a direction, right? They're ordered. So like this edge, say I name these A, B, C, and D, the arc set of this digraph. Now when I write a pair down to represent an arc, the order in which I write them down matters. So this has arc AB, BC, CD, and DA. But for instance, the arc BC is not there, right? That's a different arc. BC would be going in the opposite direction. In graphs, BC and AB are the same thing. In digraphs, those are two different arcs. They're two different edges, right? Because orientation matters there. Again, just as we often do here, here I'm abusing notation. I didn't actually, these are not actually ordered pairs. This is like a two element sequence, but you know, like formally this set is A comma B, B comma C, and so on. But we're never going to write arcs that way. It's just too much. Okay, so that's one example. Another example to re-emphasize that point that I'm making, say, I don't know, let's just do a simple triangle-like thing here. So in a graph, these two things would form a multi-edge, but in a digraph, this is perfectly okay because these are two different arcs, right? These two things are available. This is not a multi-edge. These are two different edges, right? This is edge AB and AC, that's right, BC are both here, and those are different edges, okay? So like this still allows that ED is a set of ordered pairs, like these are two different ordered pairs. So this is the first thing you're going to see in digraphs that differs from graphs. In graphs, we'd never see this thing here unless we were talking about a multi-graph where we allow duplicates of the edge. But in this picture here, this is not a duplicate, right? These are two different edges. So yeah, I mean, and if you think about it for a moment, it makes sense, right? When we're that are available to us, right? The number of edges in the complete graph. In a digraph, there's more than n choose 2 edges available to us, arcs available to us. How many arcs are available in an n-vertex digraph? how many arcs possible? Yeah. Ethan and Van here both said it. N times n minus 1, right? You can see that by choosing 2 and then multiplying by 2 for the 2 orientations, or you can see it by every arc has a start and an end, which in a graph didn't have a start and an end. It had 2 ends that were interchangeable. Okay, so there's twice as many potential ones, which is great. At every 2 vertices, there's 2 potential arcs that could be present, and in graphs there was only 1. Okay. All right, and that simple thing can actually lead to a bunch of interesting stuff here. So a couple more simple definitions. The out degree. Oops. Of a vertex V that's the number of edges leaving the vertex, okay? But it's the better way to put it here is the number of arcs VU. So that's it. It's the number of arcs VU. So the number of arcs where the edge starts in V and goes to U, so points out from it, okay? And it's denoted OD of V. A lot of textbooks will use V plus or V minus depending on the out degree. I like to avoid that because sometimes it's confusing. Like, actually, I don't remember what D still uses. Sometimes it's V minus, I think, of V. This is like the outgoing edges there. Sometimes this terminology is used. But it's so easy to mix up the minus and the plus. Is like minus out or minus in. In fact, frankly, I don't even remember. Maybe this was plus. I forget. So we're going to use ODV because it's clear that's the out degree. Okay. So I mean it's simple, but we can look here. You look at a vertex and count the number of outgoing edges, the number of edges that can be ordered in this way, VU. So here this has out degree 2, right? 1 goes out, 1 goes out. B here also has out degree 2, looks like, and C, which I didn't name, has out degree 0, right? No edges going out of it, even though it does have incident edges. Okay, so that's the out degree. The degree is defined similarly. Okay, nice. Yeah, I hope my audio is coming through here. I have a nice pop-up on Zoom here that says low system resources may be affecting your audio quality. Is audio quality still okay at the moment? So. All right. Let me close some tabs, right? That's usually something you can do. Yeah, I have this bad habit of leaving my work computer on forever. But let's see, this might help a little bit. Okay. That came at some cost, but I'll have to reopen those tabs later. Any chance that helped at all for the moment? Yeah, okay. All right. So the in degree is defined similarly. The in degree, and we define that IDV is number. Here I'm just going to write the informal way. It's the number of incoming edges. Okay. Yeah, I mean the term incoming is not used anywhere in the definition of a digraph, but I think it's pretty clear. I mean, formally it's the number of arcs UV, right? So arcs UV. So those ending in V. But we do like to use these terms incoming and outgoing edges as well. It can, it's convenient for discussing things in the graph. Okay, so now at every vertex we have an in degree and an out degree, and in this graph, let me put, just since we did it here, we did out degrees here in black, and the in degrees are here. This has in degree 2. There's 2 coming in there. This has out degree 1, I think, and this also has out degree 1 there. Okay. Obviously, the in degree plus the out degree equals what you might term the ordinary degree of the vertex, right? But that doesn't really make sense anymore because there's not edges. It's just the number of incident arcs. But we actually because the direction of arcs matters, we rarely talk about the whatever the actual degree is. But there's 2 kinds of degrees now. Okay, and in digraphs we have a handshaking lemma as well. Okay, so the lemma is handshaking. Let's just call it handshaking lemma for digraphs. And that says that, so I don't know, let D be a digraph. Then we have the following, that if you sum up for every vertex in the vertex set of D, the out degrees of V, you get the sum of V of D of the in degrees of V. Okay? The handshaking lemma for graphs said if you add up all the degrees, period, you get the total number of edges. Here I say if I add up the out degrees, then I get the in degrees here. And actually, I mean, there's a further relation I could put here as well. This is actually the size of the arc set of D at the same time. There's no 2 here. Okay? Someone want to prove this for me? This is actually easier to prove than the original handshaking lemma. Can someone tell me in one sentence why at least this equality holds, the first equality?
Is the proof every edge has a source vertex and a sink vertex?
Yeah, precisely, right? Every single arc gets counted on the left and on the right here because every single arc has like contributes 1 to the total out degree and simultaneously contributes 1 to the total in degree because like here's your edge, right? And at some point when I count the in degrees on that vertex, it counts this arc once. And when I count the out degrees of this vertex, it counts this arc once. So each arc contributes exactly 1. So actually, maybe it's even easier to see this equality by seeing that this equals this and this equals this, and therefore they're equal to each other. Okay, but it's actually like almost simpler, right? In the proof for handshaking, we said each edge is counted twice, once for the 2 endpoints. But here now the endpoints are like distinguishable, and so it like even makes it even easier to identify those things. And actually, you could use this to prove the original handshaking lemma as well by taking a graph, deciding to orient all the edges, applying this, and then undoing the orientation and seeing that like this plus this equaled this, and the total degree was the sum of these 2 guys, which would be 2 times this. It's long-winded way of doing that, but you could actually go about doing it. Okay, so that, I'm not going to write down a proof beyond that, but we do have this nice handshaking lemma for digraphs. Okay, so a couple more easy definitions. So we can talk about walks and paths and cycles in digraphs. And whenever we refer to those objects, we always mean in the directed sense. So let me write down the definition for a directed walk, which actually will look the exact same, and then just emphasize what is and isn't a walk in a digraph. And then the other 2 I'll just say that like are easy. So okay, so a directed, I'm going to put this in parentheses, walk. So when we're talking about a digraph and I use the term walk, I'm always referring to a directed walk, nothing other than that. And actually, the definition we had before works just fine, but let me just, so in a digraph so as before, it's like this concatenation of vertices, V1, V2, up to Vk, such that Vi is a vertex of the digraph, and Vi plus 1 is an arc of the digraph for all I, where that makes sense. Okay? So in the definition of walk, we had that just each Vi plus 1 was an edge. So there was an edge between the 2. Here, we still require the same. But the thing that's interesting now is like, if I write something like this is just a path, there's no repeats. But if I write this here, like this is not a walk because I need arc from here to here, from here to here, and from here to here. But between these 2 middle vertices, I haven't drawn an arc. There is an arc going the opposite direction, but that's not the arc Vi plus 1. So this thing is not a walk. Okay. Now remember, walks allow for repeated vertices, right? And even repeated edges. It's just a sequence of vertices that you go across, you just travel along edges in the natural direction, okay? And so like this term directed, we don't even need to refer to it because like we're talking about arcs. Like these things have to be there. And so like direction is important in the arc, but like it's, if you try to walk along this thing here, you're not talking about a digraph anymore. You're talking about just a regular graph. Maybe let's draw a walk, maybe go up here in one of these example graphs we did here. So like maybe I can go in blue here. So a directed walk in this one could be like I travel to that edge across that arc and then across that arc. And then I could like take this one again, right? You can always repeat things and then maybe go down here. And then actually, if you notice now the walk's done, like there's no more travel from this walk. So I went 1, 2, 3, 4. That was a walk of length 4. Okay, 4 edge, 4 arc walk. Okay. And that happened to be spanning. It doesn't have to be spanning. This, if you look at this one here, like here's one walk. That's just one simple walk there. I could also take the like longer walk by going all the way around, but I can like continue as long as I want here. Right? All those things are walks. Okay, just remember that repeats are allowed in walks of vertices and edges. They just have to travel along edges in the way that makes sense. Okay. Whereas, yeah, so keep in mind, in an ordinary graph, you could do a walk like this. You could go here, go up here, go back, things like that. That's not allowed in a digraph. Because when I traveled this direction along that edge, but that arc doesn't exist. Okay. So yeah, so in a digraph, we'll just use the term walk to refer to things like that. And so directed path and cycle defined similarly. Okay. So anybody remember the definition of a path coming from a walk? There's like a one short sentence way of defining a path in terms of walks. They can be defined, yeah, Eric, exactly. No repeats, right? It's just a walk where you don't repeat anything. I mean, we can define them without that, but that's a very short way to define them. And then what's a cycle using like maybe informally compared to a path? How would you define that in the way that I warned you guys not to do, but nonetheless, it's pretty easy to define it that way. What's a cycle? How does that differ? Actually, you could define it in terms of walks, and then you'd be fine. So it's a walk with one repeat, right? You like start and end in the same vertex, right? Sometimes you can say it's a path where the start and end of the path are the same vertex, because path would imply no repeats. I like to avoid that definition because path has no repeats. The beginning and end don't repeat. You could say a path with an edge added between the two endpoints of the path. That would work. That's a cycle. But all these things are, I mean, pretty obvious what they are. And again, they have to be directed. So like, here's a directed cycle. We had one drawn above, right? But this one's not directed. Like this triangle, say I go here, here, and here. That's not. Right, this one's clearly, I have a way of passing through all the vertices in a cycle. This one I don't, right? I go here, here, and then I'm stuck. I can't get down there. Okay. All right. So once we have those things, we can prove a couple theorems that are similar to before, but we need to introduce one more definition here. And the idea of connectivity is also a little bit different in digraphs than it is in ordinary graphs. We have two notions of connectivity. Okay, so the first, just keep writing definitions here. So a digraph D is connected if the underlying graph is connected. So what's the underlying graph? Okay, so if the underlying graph, I'll define that, is connected. Now it's pretty easy to guess what underlying graph is. The underlying graph is the graph that results if you just drop all orientations, right? And now keep in mind, the underlying graph might have repeated edges because when you have two arcs in different directions, that you get it's like, so formally it's a multi-graph, but you can just drop the extra edges, okay? Right? We almost only ever talk about the underlying graph when talking about whether the digraph is connected or not. Here, okay. So this is graph, I'll put in parentheses multi, since it can be a multi-graph, resulting from dropping orientations. Okay. I haven't actually said formally what orientation is, but it's the direction of the edge. Just ignore the direction of the edge. Replace each arc from U to V with an edge UV. And the resulting graph is the underlying graph. Okay. I mean, even just that term underlying graph, I think it's pretty obvious what we should mean there. But so we say a digraph is connected if the underlying graph is connected. Okay. So the point is it doesn't have pieces that are separated from each other. That's what it means to be connected. The truth is, though, we usually don't care about ordinary connectivity of digraphs we care about something that's called strong connectivity. And this is the true notion of connectivity in digraphs. Okay? So D is strongly connected okay. And actually, you have to keep in mind, in some textbooks, when they talk about connectivity of a digraph, they mean strongly connected. I will use this term here to make sure we're on the same page, but sometimes this is just the term we use for connected. Okay, so it's strongly connected if, so ordinarily graphs are connected if there's a path from A to B for every pair of vertices AB. In a digraph, path direction now like matters, right? Because I can get from A to B doesn't mean I can get from B to A, right? Because there's directions. And so strongly connected is just, is there a way to get from A to B and from B to A for every pair of vertices? So there and back, okay? So if for every pair of vertices, well, we used AB, so let's say AB, in the vertex set of D, there exists an AB path and BA path, okay? So you actually don't have to, you can define this a little bit differently. You can actually just say for every, or you could say for every ordered pair AB, there exists an AB path. That would imply the existence of both directions. And if you think about it that way, then you'll notice that this definition is exactly the same as the original definition in a graph, right? In a graph is like every pair of vertices, there's a way to get from one to the other. That implies the existence of the reverse immediately. But if we actually defined connectivity in the original fashion, where take an ordered pair of vertices and there's an AB path, it would be redundant, but that would actually capture this definition of connectivity immediately as well in digraphs. So we wouldn't need a separate definition. But anyway, we have this separate definition. Any pair of vertices, so you got AB, there should be some way of traveling from A to B, you know, along edges that are all oriented this way. And there should also be another way. By the way, they can share vertices. There should be a way of getting from here to here. In principle, they can share edges too. You know, I could go here, travel here, and then go back along there, something like that. But I have paths in both directions available to me, okay? And again, these, these are directed paths, right? From anytime we talk about paths in a digraph, we're talking about directed graphs. Okay, so the question is, when are we strongly connected? Because certainly the underlying graph will need to be connected. That's, I mean, obviously you can't have components there. And, but that's like not enough on its own. If this underlying graph is connected, you may not be strongly connected. And we'll see a theorem that actually explains that to us in a moment. So this is definitely a stronger condition than that. So yeah, the first theorem, both these theorems are pretty easy. That's fine. So if we have a digraph D is a digraph on at least two vertices, okay, so just say let, I don't know, this isn't how I meant to write it, but that's fine. So D is strongly connected if and only if there exists a closed spanning walk in D. Okay, let's remind ourselves real quick here. So we know what a walk is. It's just the sequence of vertices that between any two consecutive vertices, you have an edge, V to VI, VI to VI plus 1. Spanning means that walk uses every single vertex at least once, right? Walks can repeat, so it uses, so all vertices appear. And closed means it starts and ends in the same vertex. Okay, start equals end. Yeah, starting point vertex equals the ending vertex. And this is all vertices appear. And walk is, we defined walk a moment ago, okay? So this is, I mean, this can actually be taken as a definition, basically. I mean, it's an if and only if, of course, but let's go through a simple proof here. It's pretty clear that it works, I think, already, but okay. So first off, let's suppose that D has this object. It has a closed spanning walk. So there exists a closed spanning walk in D. And I want to convince myself that it is strongly connected. So why is it strongly connected? Well, we have to find a UV and a VU path for every pair of vertices. So find a UV and VU path. Okay, but that's easy, right? Sorry, okay. We need to find, yeah, that's what we need to find. How do we actually find this? So there's one part of this that's going to be an exercise here, but how do we find such a thing? What do we definitely have? We're looking for a VU and a UV path. What do we have that's almost those things? All right, we've got our digraph D here. And here's U, and here's V. Is there some way to travel from U to V here that may not be a path, but some fashion? Yeah, I mean, there's a closed spanning walk here. So that closed spanning walk eventually arrives at U, and it exits U, and it goes all over the place, potentially repeating vertices, potentially repeating edges, but it eventually hits U and continues on. I mean, it eventually hits V, and continues on and goes back to V, right? This thing definitely exists. So there exists a UV walk and a VU walk because of the fact that there's a closed. It's crucial that it's closed, and it's crucial that it's spanning, right? Spanning means if I take any two vertices, they will be included in the walk. And closed means that if I start at U, I can get to V, and if I'm at V, I can get to U. Like if it's not closed, I might only get one direction here, okay? And then the exercise is, and we actually already proved this ordinarily, but if you have a UV walk, then that implies the existence of a UV path without repeats, right? And then the proof is, I mean, I'll just tell you, it's take a shortest UV walk. And that'll mean, like, if there were repeats, skip the repeats, right? We actually did this for ordinary walks, like I think the first or second day of class, okay? So the exercise says, then there exists a UV path and a VU path, which is what we want, right? We need to find those paths in order, so then D is strongly connected, okay? So that's the end of that direction. That direction's trivial. Actually, sometimes textbooks define connectivity in graphs and digraphs by just asking for the existence of a UV walk instead of a UV path, because once you have the walk, you definitely have the path, and so it works there. And so it skips this minimality step there, but I think that's a useful exercise anyway. And frankly, most textbooks define it in a path, not a walk, but nonetheless, defining it with a walk is fine. Okay, now the opposite direction is a little less easy. So now we're strongly connected. How do we find this cool spanning structure that hits everything, okay? So D is strongly connected. And actually, so yeah, I said it's a little bit harder. It's not harder. The proof here is actually rather amusing to me here. So it's strongly connected. How do we find a closed spanning walk of the entire graph? Well, watch this. If it's strongly connected, then for every pair of vertices, there exists an AB path. So let's just do the following. Let's say, so there exists the following paths. There's a V1 to V2 walk, right? There's a V2 to V3 walk, a V3 to V4 walk, and so on, eventually to the Vn-1 to Vn walk. And then there's also a Vn to V1 walk, right? All those walks exist. So, I mean, what does this look like? Say my vertices are all arranged in a long line here. Okay, I'm going to draw this in a completely unreasonable way, but there's a walk from the first vertex to the second vertex. So it looks something like this. Now, that walk only, these are all the vertices, so there's nothing out here, but I don't want to like draw it crossing over here because it's horrible. Okay, maybe I'll do it for the second one here, right? So it goes in, uses vertices here, and comes back to that one. And then this one, so that goes from here to here, this one goes from here to here, then this one goes in here, mixes up, it might even go back, and then goes there. But if you just concatenate all these walks, it tells you, oh, here to here to here to here. Okay, like it's out of control already, right? But like that will eventually get me from V1 back to V1, and it will necessarily travel through all the vertices. It's almost certainly not going to be a path. There was going to be horrible, horrible amounts of repeats, but who cares, right? We're looking for a actual spanning path, a spanning walk, right? So, you know, walking along all these paths sorry, walks gives a closed spanning walk of D. That's it. And you could maybe be more efficient somehow here to avoid some repeats, but you know, that's not what we're trying to do here. Okay, so it's very simple. You just concatenate all the walks, each of which exists. Okay. All right, so let's actually prove a more interesting strongly connected theorem here. And we need one more definition here. And this is a special type of digraph. This is a digraph that's called an orientation. Okay, so an orientation. This is another definition. So an orientation of a simple graph G. Simple here is to re-emphasize that we're talking about a graph. The term simple actually means that it's not a multi-graph. That's what simple means. So we usually don't need this term at all. And actually, you can do an orientation of a, you know what, I'm going to erase that, because you can orient a multi-graph as well. I didn't say it, but multi-digraphs certainly exist as well, right? You can allow repeats of an individual arc, like and you can even have loops. You can even have loops in a digraph as well, right? The loop starts at a vertex, goes out and goes back in. So all that stuff's allowed, but we're not going to use any of that for now. So an orientation of a graph G is a digraph D that results from, in quotes, orienting each edge of G. What it means is each edge of G is replaced with an arc between those two vertices. There's two choices for the orientation of that edge, right? It can go from U to V or from V to U. So there's multiple orientations, okay? So the of graph G is a digraph D resulting from replacing each edge, say UV of G, with either arc UV or arc VU. Okay. So that replacement here this is the orientation of UV. So, you know, again, to use our C4 example, here's G, and there's multiple orientations of this, right? I mean, if it's labeled, there's going to be 16 orientations of this, depending on the direction I choose. If it's not labeled, then there's like some issue of like isomorphisms, and you have to count how many there are, and that's not something we're going to do. But one orientation would be, okay, choose a direction for each edge. I choose that edge to go in that direction, that edge to go in that direction, that arc, sorry, to go in that direction, and that one. There's one orientation. But there are others, of course. Okay, I don't want to draw on the same picture there. Right, but each arc has two choices. Maybe I do the same one there, different one there, something like that. There's a different orientation. Okay, that's all an orientation is. Take the edges, choose a direction for them, choose an orientation for them. Okay, so now we have like an interesting, although still not hard to prove here, theorem here. So when is an orientation two connected? So I have a graph, I orient the edges. When is that resulting graph strongly connected, right? When did I make it like a good choice to make it strongly connected or not? Actually, I think these two examples, neither was strongly connected. Yeah, okay. I think were neither of them, like, I don't know. So let's look real quick. Like this, yeah, this vertex here, for instance, right? This is like almost, you can almost think of this as like an isolated vertex here. This has no outgoing edges. I'm not going to be able to get from here to anything else. So that's not going to be strongly connected, right? There's no V whatever path here. And this one probably also, yeah, this one failed for the same reason here. Is there a strongly connected orientation though of this graph? Was there a smarter way to orient it so that it was strongly connected?
Cycle.
Yeah, exactly. Orient it as a directed cycle. Thanks, Brad and Ethan. So this one, oh, very nice, right? And actually, we'll use this idea in our proof in a moment here. Any two vertices, right? These two have one, there's clearly a UV path, just the arc itself. And what about VU? Yeah, travel around the rest of the cycle. V goes around here and ends up in U, right? So cycles are clearly strongly connected. Yeah, strongly connected. So this is a strongly connected orientation. But not every graph has a strongly connected orientation. Some do, some don't. Okay. There's one obvious reason why a graph would not have a strongly connected orientation. Can anybody identify one? So I give you a graph and say, hey, can you orient this and get a strongly connected graph? Tell me a witness for the fact that like there's no chance of being able to do that. Yeah, so vertex of degree 1, that's good, Eric. A leaf, yeah, same thing, Max. So that's good, right? That's like if you have an edge that looks like this and like other stuff in your graph, strongly connected orientation is out here. We can say something a little bit stronger than this. Bridge, yeah, Brad, very good. A bridge is actually even more, right? Like, so we don't even need degree 1, but if you have this bridge here, like just think for a second. If I orient it this way, there's no way to get from a vertex here to a vertex here. And if I oriented it the other way, obviously there's also something. In fact, I can even just look at the two end vertices of that. There's not going to be a path in the reverse direction. The other obvious thing is like the underlying graph ought to be connected. Like the graph I give you to orient should be connected, but we're going to assume the graph's connected. It turns out the existence of a bridge is the only impediment. So whether or not you have a bridge precisely determines whether you're strongly connected, whether or not you have a strongly connected orientation or not. Okay, so this is sort of the obvious necessary condition. Turns out it's sufficient. Okay, so let's state the theorem then. So let's just say that we'll start off with let G be a connected graph, right? As we said, if we give you G and it's not connected, then strongly connected orientation is out of the question completely, so we won't even discuss that. So then the theorem is G has a strongly connected orientation. Okay, I'm going to give this shorthand. This is going to be an SRO, strongly connected orientation. We're going to use this term in the proof a bunch of times. I don't want to write it out 100 times. If and only if G has no bridge. Okay. So if there's no bridge, then there is a strongly connected orientation. Okay. Proof. Well, we actually proved one direction already, right? We already proved that if there exists a bridge, then no strongly connected orientation possible, right? We already did that direction because if you look at this picture again here and you have a bridge, then it's clear that no matter how I orient this graph, there's going to be a vertex here and a vertex here for which there's either not a UV path or not a VU path. It just depends on which direction I orient. The opposite direction will be impossible. Okay. That's if it has a bridge. So that means if it has a bridge, then it's not strong. It has no strongly connected orientation. Okay. So that's this direction here. Okay. So now let's prove the other direction. Let's say that it has no bridge. Right. This is the contrapositive of the first direction. Okay. So now, suppose there is no bridge in G, and then we want to find, oh, this is funny. Yeah, I never used that before, but yeah, want to find, what do we want to find? Well, okay, we want to show, actually, that's too bad, but we want to show that it's strongly connected. No, we do, sorry, we want to find a strongly connected orientation of G, right? We actually want to produce it. Oops, come on. Why? Oh, whatever. Okay, so we're going to use a trick we've used before in connectivity and a lot of other places. We're going to look for this maximal substructure idea. Let's find the biggest thing in there that does have a strongly connected orientation and show it actually is everything. So we'll do it by contradiction. If it's not everything, then something that's missing we should be able to add somehow. Okay, so let's let And I've written this a little bit different that's in the notes. I'm gonna change the notes to reflect. This is the same argument, just a little bit different terminology. Okay, so let H be a subgraph of G. So be this is actually going to be vertex maximal. Although this we can actually just throw out vertex maximal. So I maybe haven't actually emphasized this clearly enough in this class yet. But when I talk about a maximal subgraph, it means a subgraph of G that is not contained in another subgraph of G, right? There's not a larger subgraph that contains it. That's what maximal means. So what it means is that if I add any edge to it, or even any vertex in an edge, then that graph will have this property that I'm claiming it doesn't have, okay? Like last time we said that we were edge maximal and not having a matching. That meant when I added an edge back in, I got a matching, a perfect matching, okay? So this is a vertex maximal subgraph of G that does have a strongly connected orientation. Okay, so take a subgraph of it that does have a strongly connected orientation. Now, in these problems, there's always two things to do, right? One, we're going to hopefully find a contradiction at some point that if H is smaller than G, somehow I could make it bigger, and that would be a contradiction. But in order to even get there, what do I have to actually do first here? I have to answer a question here to like even start. Like, by the way, these vertex maximal type problems here, maximal subgraph questions, these are induction in disguise, okay? So I have to start do like some sort of base case. But you don't have to think about induction here. What I have to do is show, is H even a thing? Like, is it empty? Like, if it's empty, I'm not going to be able to do anything. Like, I'm not going to be able to add to it. So I need to show first that does H even exist? So is there even a subgraph to begin with at all? Forget vertex maximal, just is there a subgraph that has a strongly connected orientation? Sometimes this is trivial, sometimes it's not. Why does this have one? Does anybody see a subgraph? What would be a really nice subgraph to look for that easily has a strongly connected orientation? We did one already, right, Ethan? Yeah, Brad, yeah, says a cycle. Yeah, so is there a cycle? Like, a cycle is easy to orient, right? We know if we can find any cycle, we already know how to orient it. Just do the sort of natural directed cycle orientation, and that will be a strongly connected orientation. So H exists if we can find a cycle in our graph. Does our graph have a cycle? So G is connected. That doesn't mean it has a cycle, but G also is what? G has no bridge. If you have no bridge, then you have to have a cycle. I think maybe we've even proved this directly at one point, probably in the trees section here. But let's say bridgeless graphs have cycles. Okay, you can prove this if you want by walking. Start at a vertex, there's no bridge, so I can always continue my walk, and I won't ever get stuck, and I won't ever. But I may repeat eventually. But as soon as I repeat, right? Say I like do something like this. Well, fine, I found my cycle there. The only way I wouldn't be able to return is if the bridge existed. This is a maybe slightly hand-wavy way of proving this, but we have cycles. Okay, once we found a cycle, we know how to orient the cycle there, and so that means that G does contain subgraphs that have strongly connected orientations. So there is a vertex maximal one, right? It might not be a single cycle, it might be something bigger, but there definitely exists one. Okay, for instance, I think like this one here actually has a strongly connected orientation, even though itself is not a cycle, like there's extra edges. Okay, we're just gonna have cycles, and cycles have strongly connected orientations. Okay, so great. So yes, H exists. Okay, there is definitely some H. All right, and so let's look at a picture, and then basically the proof is finished. So let's look at H. This is H. So if H equals G, then done. Actually, we don't even need that. Let me just say this. We need something even weaker is all we need. If the vertex set of H is the entire vertex set of G, Even if you're missing some edges, then you're done, right? If I find a strongly connected orientation of some of the edges of G, adding in a few extra edges, like, only helps me. I already have a UV path for every pair of vertices. Like, if there's a few edges I didn't bother to orient, I didn't even need them. So all I have to do is find a spanning subgraph that has a strongly connected orientation. I don't even need to orient every single edge. Like, those edges that I didn't need to orient, just flip a coin. Who cares? Okay. So if V of H equals V of G, we're done. So suppose not. Okay. So suppose that V of H is a strict subset of V of G. So that means there's like some vertex over here. So here's H, and here's some vertex that's not in H here. Okay. So the graph is connected. So there's definitely an edge here. That edge of some sort exists, right? That exists. So exists as connected. What else exists though? Yeah, there's some way of getting from V back to H because there's no bridge. This is not a bridge. So that means that I can keep walking out of here and eventually I will return to H. Now it's possible that return is actually back to U itself. I said there's no bridge. I didn't say there's no cut vertex. There could be a cut vertex, but that actually doesn't matter here because now what can I do in this picture here? What if I orient this extra piece here like this? Just in the natural fashion. Everything in here, by the way, is oriented already or has a strongly connected orientation, right? There is a strongly connected orientation. So take that orientation and add to it the edges here oriented this way. Okay, so add these arcs in red here to H to get H prime. Now, what can you tell me about H prime? So this new graph is H prime. It's all of H plus at least this edge. And actually, I need at least one more edge to get back. It's possible that I immediately go back. But now, this graph is strongly connected, right? Let's just quickly examine. If I take two vertices inside of here, there's definitely a way from getting from A to B already and B to A. That's by the strongly connected orientation. If I take two on this cycle, so say I take this one and this direction is clear. The other direction is maybe not completely clear, but it's not hard either. I take this one, go in here, and then from this vertex, there's a way to get to that vertex. Or they're the same vertex, that's possible. And then I continue on this cycle here to V, and that finds that direction. And then the final case is if there's one vertex in here and one vertex here, and that's also clear. I have to walk from here to here, and then walk from here to here, which exists. And then the reverse, I have to walk from here to here, and then walk from here to here, which exists. Keep in mind, those two paths, the UV and the VU path, they might share vertices with each other. It doesn't matter. Like, they just have to both exist, okay? So, but H has a strongly connected orientation and is bigger, right? That's a contradiction to the vertex maximality of H. And so we had to be in this case here, right? It contradicts this suppose not. The standard trick there. You can grow the maximal subgraph here. Okay. All right. That's the end. I'm done for today. We're right on time.